So this video is going to give a bit more detail to one of the examples on mathematical induction in the lecture notes. So what we're asked to do is to prove that for all natural numbers n, the sum of the first n squares is given by the formula 6th n, n plus 1, 2n plus 1. So let's look at the proof. So we're going to use proof by induction. So we need to define our Pn, our predicate here, and it's just going to be the line above. So we'll define Pn to be the statement sum of the first n squares is a 6th n, n plus 1, 2n plus 1. So as usual, we break the proof down into two steps, and the first one is to do the base case. So this is just looking at P1, so this is for all n in n. So if we consider P1, so now we just take this expression and put n equals 1 into both sides. So on the left hand side there's only one sum in the term in the sum, so it's 1 squared, and we replace n by 1 in the formula, and that gives us a 6 over 6, that's obviously 1, and so that means P1 is true. So the predicate here with n equals 1 is a true statement. So then we move on to the inductive step. And remember, that means that we take a natural number, call it k, and we're going to try and show that pk implies pk plus 1. So assume pk is true. And that means that we can assume that the sum of the first k squares, so that's going to be 1 squared plus 2 squared plus dot 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 plus k squared, is given by the formula when we place n by k, so that's equal to a 6th k, k plus 1, 2k plus 1. So we need to show now that given that assumption, it follows that pk plus 1 is also true. And that means that the corresponding formula with k plus 1 here instead of k throughout the expression is also true. So how do we get from this to the same expression with k plus 1? Well, we need to add k plus 1 squared to both sides. So let's do that. And see what happens. Well, if we take the left hand side and add k plus 1 squared, so we've now got the sum of the first k plus 1 squareds. Then do the same to the right hand side, just add on k plus 1 squared. And now we have to show this is equivalent to the formula with k here replaced by k plus 1. So we need to do some algebra. So if I take out a factor of a 6th k plus 1, I'm left with k times 2k plus 1, and then I've got 6 times k plus 1. And if we carry on simplifying, inside the main bracket here we get 2k squared plus k plus 6k, so that's 7k plus 6. And that quadratic factorises conveniently into k plus 2 and 2k plus 3. And if we just rewrite this slightly so we can see exactly what's going on. So we can write the k plus 2 as k plus 1 plus 1, and we can write the 2k plus 1 as 2k plus 1 plus 1. And remember, this is all equal to the sum of the first k plus 1 squares. But this now, of course, is the formula we had. This is Pn with n equal to k plus 1. So it's the original formula with the n replaced by k plus 1. So therefore, we've shown that pk plus 1 is true. And that was our inductive step. So we've got the base case, P1 is true. We've shown that pk implies pk plus 1, the inductive step. And so now, applying the principle of induction, Pn is true for all n in n, which is what we set out to prove, and so we've completed the proof.